In this video, we're going to look at how entropy is quantified and how we can use it in calculations to determine whether entropy favors the reactants or products of a chemical reaction. First off, let's look at the laws of thermodynamics, which govern principles behind how both entropy and enthalpy works. Premise number 1 states that the total energy in the universe is constant, meaning that energy cannot be created, nor can it be destroyed. We only have the ability to convert energy between one form and another, and that includes between enthalpy and entropy as well. Premise number 2, which we were exposed to in the previous video, states that the total concentrated or organized energy of the universe is in a constant decrease, while the total diffuse energy, disorganized energy, tends to constantly increase overall. What this means is that the entropy of the universe overall is on a constant upward trend, and observationally, obviously we can't look at the entire universe and observe the trends that occur, but we can look at the change in entropy within an isolated system, which is how we introduce the concept of entropy. In short, within an isolated system, if we cut off all energy and matter from the outside, entropy never spontaneously increases, and overall, we see a movement from a more organized state of matter to a more disorganized state of matter, and this is why diffusion occurs regardless of whether the system is open, closed, or isolated, and from that we can extrapolate outward and say that entropy in the universe has an upward trend and tends to increase overall. That brings us how to quantify entropy mathematically. So we use the variable S, let's write that more neatly, S, to represent the numerical value of entropy, but just like with enthalpy, where we aren't really interested in the amount of thermal energy in a reaction, the more interesting variable to study is the change in entropy, which we represent with the symbol delta S. In general, just like how delta H can be represented as the energy change between kinetic and potential energy, we can represent delta S as being the change in enthalpy that occurs in the universe. Now, within chemical reactions, there are only really two parameters that matter. Number 1 is the change in entropy that occurs within the system in which the experiment takes place. So a chemical reaction is either going to favor a more disordered form, in which case entropy increases, in which the reaction releases entropy into or out of the system and into everything else, which is what we call the surroundings. Or if a reaction consumes entropy, it's going to absorb entropy from the surroundings in order to drive the reaction within the system. And this is what we mean by delta S. For principle number 3, this is where we can actually approach how to numerically quantify entropy. So one trend that is observed is as the temperature of a given substance approaches 0 degrees Kelvin, which we also know as absolute zero, the lowest possible temperature at which basically all particulate motion stops, the entropy of that given substance approaches a constant number. Now, this number is different depending on what the substance is, because all substances, depending on their state of matter, their atomic mass, their number of bonds, have a different amount of entropy associated with it. But we can use these constants in order to give each element and compound what we call the standard molar entropy. And this measurement basically tells us exactly what this number represents. It represents the amount of entropy that a given substance has per mole of that substance at specific conditions. And again, those specific conditions are normally standard atmospheric temperature and pressure, just like what we use with standard molar enthalpy of formation. And as we would expect, the standard molar enthalpy of a given substance is labeled with the variable S0, or S with a superscript degree sign here, listed in joules per mole of the substance per degree Kelvin that is increased. This allows us to use standard molar entropy in order to calculate the change in entropy from the reactants to the products exactly the same way that we would calculate delta H of reaction. So similar to delta H of reaction, we can calculate the standard molar entropy change of a chemical reaction simply by following a formula that looks very similar to the formula of delta H, where we take the sum of all of the standard molar entropy of our products and we subtract from that the sum of the standard molar entropy of all of our reactants. And depending on whether the number is positive, meaning that our products have a greater entropy than our reactants, or if the number is negative, if the opposite is true, that will tell us whether entropy favors the products or the reactants of our reaction. So if we go ahead and use these numbers, which came from the same thermochemical data table we used before, we can calculate mathematically whether the forward or reverse reaction of the synthesis of water is favored. So if we go ahead and do that, we know that water is our only product, so the sum of all of our standard molar entropy of reaction is going to be the sum of the products, which is 2, because we have 2 water molecules, times water's standard molar entropy, which is 188.72. And from that, we're going to subtract the sum of all of our standard molar entropy of our reactants, hydrogen and oxygen. So again, we have 2 times the standard molar entropy of hydrogen, which is 130.59 joules per mole per degree Kelvin. And we're going to add the standard molar entropy of oxygen gas, 205.03. And if you put this into your calculator, you should get negative 88.77 joules per mole of chemical times degrees Kelvin. So because this number is negative, therefore we can conclude that the sum of the standard molar entropy of our reactants must be greater than the sum of the standard molar entropy of our products, and therefore that means that as we move in the forward direction, entropy actually decreases. So because entropy decreases from reactants to products, that means that entropy cannot favor the forward reaction, because the second law of thermodynamics states that increasing entropy is always more favorable, and therefore it must be the reverse reaction that entropy favors. And that's exactly what we see, because if we count the number of particles, we see there are only 2 product particles, whereas in the reactants we have 3. So it makes sense that entropy favors the creation of the reactants rather than the products. This concludes the video series covering entropy. In the next video, we're going to look at how trends in dynamic equilibrium reactions can help to predict whether we are going to get more products or more reactants, assuming that we have a reaction working in both directions.